Okay, in this video, we're going to talk about the different reaction types and get ourselves set up to do a lab experience with that, okay? So first of all, we want to talk about how many reaction types do we have, and we have 5 of them. And each reaction type is going to have a similar pattern to it, okay? So as we look at each type, we're going to go through how does it pattern out. We're going to see an example of it and also show us how we can identify those different reaction types based off those patterns, okay? There are 5 types. They are combination, decomposition, single displacement, double displacement, and combustion is what we'll be looking at. Now, our first reaction type is kind of this idea, if you have 2 things all by themselves, 2 single things, we can put them together and combine them to make a compound, okay? So we call that type a combination reaction. And our general pattern is A plus B yields AB, okay? Now, each letter in the alphabet, the A and B, those represent individual elements, okay? So A would be an element, B would be an element, and we make the compound AB that's now combined together. Notice how we have a plus sign between the A and B. That tells you that they are independent elements. Here we do not have the plus sign, so that tells you that these are combined together in a compound, okay? So looking at this general pattern, how we would identify this then is we're going to look for our reactants, or our left-hand side, to be 2 elements. They could be diatomics, so it's possible you might see O2, F2, H2, something like that there as one of our elements. And then on our product side, we'll see a single compound, okay? Now, here's our example. We have aluminum, which would be our A, reacting with iodine, which would be our B, to produce aluminum iodide, which is our AB, okay? You'll see a lot more information in this reaction. We have a 2, a 3, the states of matter. We see heat being let off. All that stuff is great information, but it doesn't distract us or shouldn't distract us from the basic pattern, which is one element plus another element making a single compound, okay? So this extra information is necessary for the chemistry, but not for identifying the reaction type, okay? Same thing with the coefficients, the 2, the 3, and the 2 here. They're there to balance our equation. They play no role in identifying the type of reaction we have, which is a combination reaction. Okay? When we get to lab time, we'll be doing something very similar. We'll be taking magnesium and reacting with oxygen to make some magnesium oxide. But that's our combination reaction type. In our decomposition reaction type, that's our next type. So if we can take 2 elements and put them together, we can also take a compound and split it apart. Okay? So decomposition is the exact opposite of combination, where we start off with a single compound and it breaks apart into individual elements. Now, it could be more than just 2, okay? So decomposition can be more complex, meaning the compound could break apart into several things on the right-hand side, okay? But it always starts with a single compound, okay? So that's one of your best indicators, or how you identify these, is it's only gonna have a 1 reactant. And I would probably add 1 reactant as a compound here, because it's not an element as a reactant, it's going to be a compound is one of our reactants here, okay? And it's going to decompose into 2 or more products, okay? So here's our example. We have ammonium dichromate, actually ammonium dichromate. It's a really complex compound, and it has lots of different elements in it, but when it decomposes, it breaks down into nitrogen gas, some water, and some chromium oxide, okay? So we see that we get 1, 2, 3 different products. They're much smaller, less complex than this. One's an element, and 2 of them are also more compounds, but they're still smaller things. So this would be a really good example of a complex looking decomposition as we take a look at it, okay? So the AB would be this whole thing. So all of this would be A, all of this would be B, and then we have A plus B plus C in this setup, okay? So that's decomposition. We start with 1 compound. That's your best indicator, making 2 or more products. What we're going to do for our lab time is we're going to decompose aqueous hydrogen peroxide in solution to make water and oxygen gas. Now our next reaction type is called a combustion reaction. Combustion reactions are very unique in their setup because they're not going to be very generalized. What I mean by that is we're going to have a very, very specific pattern to them. So it's not going to be allowable for us to use just any elements. We need to use very specific elements for combustion reactions. So for combustion reactions, we're going to take a hydrocarbon, and we'll talk about what that is in a second. We're going to react it with oxygen. We're going to always make carbon dioxide, always make water, and always make heat. Okay, so if you notice, it's different than the decomposition or the combination where we are very general here, A's and B's and that stuff. For combustion, it has to be oxygen, it has to be carbon dioxide, it has to be water, it has to be heat, okay? The only thing that can change is the type of hydrocarbon, okay? So hydrocarbons are any compound that are primarily made up of carbon and hydrogen and maybe one oxygen inside them, okay? So if you're looking for a hydrocarbon, you're looking for this grouping of like C3H8 or CH4 or C8H14 or C2H5OH or C3H7OH. Something that looks lots of hydrogens, lots of carbons inside there for your reaction, for your reactant. Now, combustion is what you think it is. This is basically burning or explosions is what we're talking about, but it's specific to hydrocarbons, okay? Now, other thing we want to make note of is that we're going to make the same product. So we're going to make carbon dioxide and water and heat in all of them, all right? So when you're trying to identify a combustion reaction, we're not looking for A's and B's. We're looking for this pattern of O2, CO2, and H2O. And it has to be that the H2O and CO2 are in the product side or on the right-hand side of our arrow, okay? If you see the water and carbon dioxide on the reactant side, that's something completely different. It's not considered combustion as we do this, okay? When we get to lab, we're going to be taking some ethanol and we're going to be combusting that, obviously with oxygen, to make our carbon dioxide and water. Now, the next reaction type is called single displacement. Single displacement reactions are a little bit more complex because now we're going to start trading partners, okay? So in a single displacement, we're going to have element A and a compound we'll call BC. And A and B are going to switch places with each other, okay? And A will be a metal and B will also be a metal in this scenario. So A and B are going to switch places with each other. So B will end up being alone and then A will end up being the compound, okay? So I often think of this as like you have a person who's a single person and you have a couple who are dating and the single person steals the boyfriend or girlfriend from the person that's being dating. So then they end up being alone and then you make a new couple from that, okay? So we now have covered lots of reaction types. We've talked about two things combining to make one thing. We've talked about two things splitting apart. We've talked about combustion. And now we have a scenario where a single thing trades partners out with the compound. Okay, so in our example, we see aluminum again. That's going to be our A. Copper is going to be our B. And chlorine is going to be our C. And aluminum and copper are going to trade places. So copper ends up by itself, and aluminum ends up in the compound. Okay, you'll notice some little things like the subscripts could change. The states of matter can change. None of those things are going to really affect how we identify the reaction types because our general pattern still holds. We have a single plus a compound making a different single plus a new compound, okay? This is also the first time we see the same pattern on both sides of the reaction. So we have a single plus a compound and a single plus a compound on both sides of the reaction for identification, okay? So our reactant side, we see that. In our product side, we see the single metal plus ion compound, and they're switching. One thing to note that this chemistry is almost always done in solution. So we have these things dissolved in water to allow the chemistry to happen, okay? In lab time, we're going to take hydrochloric acid, we're going to react that with calcium, and we're going to make calcium chloride and some hydrogen gas, okay? And in this case, the hydrogen is going to act like a metal here as part of our process, all right? So that is single displacement. In our last reaction type, we have double displacement, okay? And double displacement is very similar to single displacement where there's going to be a displacement of metals, okay? But in this case, we call it a double because both things start in compounds. So we have a compound AB plus a compound CD, and the C and A again are going to switch places. The two metals again will switch places. So we end up with CB and AD, okay? So looking at our kind of example, A would be our lead, B would be this nitrate combination, C would be the potassium, D would be the iodine. So we notice how lead was with NO3, K was with iodine. On this side, the K is now with the NO3 and the lead is now with the iodine. So they have switched places between each other, okay? So in this type of chemistry, we have two things in compound, both in solution, and they're happy there. They're fine in solution. But when you mix these two solutions together, one of those two compounds ends up forming a solid, and then that leaves the reaction. And as a result, this thing drives the chemistry forward, okay? So again, we're looking at this idea of what's our reactant side. It's ionic compounds plus ionic compound, and the products are going to be the metals are going to trade partners to make new ionic compounds, okay? In terms of our pattern, again, we see the same pattern on both sides. So we see two compounds on the reactant side, on the left-hand side of our arrow, and two compounds, different compounds, on the product side of our arrow, okay? These are always done in solution, okay? There are some cases it doesn't, so always is a strong word there. But for the most part, anything that we're going to see these done in solution. So these reactions will be done in solution. Okay, and then once we get to lab time, we're going to use some copper nitrate. We're going to react it with sodium hydroxide and have them switch partners, and then we're going to hopefully see that solid copper hydroxide precipitate form. Okay, so the last slide we want to take a look at here is we're looking at identifying the reaction types. And if we take a look here, we see we have 5 different reactions, and we have our combinations here. So we want to match them up. So here I have a compound, two elements together plus two elements together. So two compounds as reactants tell me that this has to be double displacement. Okay. At this one, I have a single element and I have a compound, and then I have a compound and a single element. So I have a single plus a compound. Single plus compound tells me I'm going to be single displacement. Here I have single element plus single element and one compound being produced. So that tells me it's combination. Here I have carbon and hydrogen, which is the compound, with plus a single. So I have a compound plus a single, but wait a minute, that single is oxygen. That reminds me of something. And I'm making carbon dioxide and water and heat. Oh, wait, that's a special pattern because carbon dioxide plus water plus heat was part of those combustion reactions. So I go back to my compound, and yeah, that compound is a hydrocarbon. So I have a hydrocarbon plus oxygen making carbon dioxide, water, and heat. So that's going to be one of my combustion reactions, okay? Sometimes single displacement like this and combustion look a lot alike because they both have a single and a compound. That's why we have to identify that hydrocarbon and the carbon dioxide and water to help us out. And then last but not least, I have a single compound right here, one compound breaking apart into two other things. So that would be my decomposition reaction. All right, so that is reaction types. Thank you.